And welcome once again, Calculus 3 students. We are going to extend our definition of local max and min to 3 dimensions. Pretty exciting stuff. Let's look at the graphic here because this if I have the visual it will help. I can see that this point up here at the top is a local maximum and an absolute maximum over the entire function. This point here is a local max relative to those other points in his neighborhood, and likewise on the minimums. Just as in our 2 dimensions, in 3 space, we are going to be looking at where that first derivative equals 0, and in this case it's where the partial derivatives equal 0. So notice our definition for critical point. The critical points are those places where my partial derivative with respect to x and y are equal to 0 or fails to exist. So in example 1, I'm to find the critical points of the following function. Now first I do need to say that it is differentiable on all points of my x and y, and after that I'm to do the partial of x and the partial with respect to y, so I'll do that. Just a quick run through of what I did here. I used the product rule and I took the derivative of the first, left the second 2 alone. Then I took the derivative of the second, left the others alone, and then I took the derivative of the third. There's no x in there, so that would be a 0. Remember that I was treating the y as a constant in all cases, and I'm going to do the same thing for y, but then it was just a matter of manipulation, and this was what I ended up with for my partial with respect to x. Next, I need to identify the places where the partial derivatives where the partial derivative of x and the partial derivative of y equal to 0. So I have to start with one of them, so I'll just go ahead and start with x, and I'm going to say that that occurs when y equals 0, x equals 1, and y equals -3. Now that's for the first one, but it also has to be true for the second. So let's see what happens when y is 0 for this second partial. So when y is 0, then we'll write down what we have. I think I'm going to separate this a little. Okay, so I've worked this for my first one. I plugged in my y equals 0, and I found that this would happen at the point 0, 0, and at 2, 0. So these 2 points are critical points, and I'm going to do the same thing for the next 2. Alright, so I got this value, and so the point 1, comma, -3/2. When x is 1 and y is -3/2, I would have a critical point. And there we have it. We have 5 critical points for this particular equation in 3 space. And I might want to add that the critical points are the places where I can have maximums and minimums, and then I need to do a test to see if it is a maximum or a minimum. Let's look at a saddle point. A saddle point is one in which if I look at it in one regard, then all those points around it are greater than that point, and if I look at it from a different perspective, then all those points are less than that point. And that is going to be defined as a saddle point, and of course here's the formal definition here, where those points are greater on one realm, and then those points are less than on looking at it from a different perspective. The second derivative test allows us to determine whether or not a point is a local max or a local min, and also whether or not it is a saddle point. So if you remember back from Calculus 1 with the second derivative test, we were able to determine whether or not it was concave up or concave down. So we're going to start this by finding the partial derivatives with respect to x, and we're going to find the second partial with respect to x and the second partial with respect to y, and then the partial with respect to x and then y. Okay, I have found the critical point for this particular function that I have, and now I'm going to find the discriminant by plugging into this right up here. Alright, this is what it's going to look like. Now I'm just going to plug into my different equations and what I got and get my value. Alright, I got an 8 for my discriminant, so let's go up here and look and see what my options are. My options are either 1 or 2, and the value of my partial with respect to x on that second partial is a 2, so it is greater than 0 and my discriminant is greater than 0, so that means therefore f has a local minimum at that point to -1. Nice. Alright, this is the same exact problem as we were given in example 1, and we found those critical points in example 1, so I've just listed them, and then I found those partials. The next thing I'm going to need to do is find the value of the discriminant at each of these critical points and figure out exactly what this critical point is, if it is a maximum, minimum, saddle point, or something that's neither. Alright, so here we go. Alright, so on my first one I got a -36 for my discriminant. That means my discriminant is less than 0. If it's less than 0, then I've got a saddle point. So this is a saddle point. I'm going to go down and do this for the rest of these, just doing those computations over and over. Alright, using the second derivative test, I have determined what happens at each of these points. Looks like the first two and the last two are both saddle points at each of those locations, and this point here, 1, -3/2, is going to be a local max. Here's a groovy little picture of our local max surrounded by our 4 saddle points. For our next problem, we are to find the dimensions of a box that has the largest volume. I do know that x plus y plus z has got to be 96 or below, so I'm going to rewrite this so that I can just have 2 variables here. So I'll just say that z equals 96 minus x minus y, and our volume equation then in terms of x and y would be x times y times this z, which is 96 minus x minus y. Next thing I'm going to need to do is I'm going to have to get the partials of each of these so that I can find some critical points. Alright, in doing the computation for this, I get these 4 critical points. Now note that I did have to check the boundary points for this because this doesn't continue on in all directions, so I do have to check those boundary conditions, and that's why those points are there. Alright, so next thing I'm going to do is do my second derivative test. So I'm just going to compute my discriminant and plug in from there, because remember, I am looking for the maximum. Alright, and you can check out all of the points. However, when I check out the point 32, 32, I will find that my discriminant is greater than 0, and the value of my second partial with respect to x is -64, so that would be less than 0, and using my second derivative test I would find that the point 32, 32 is my maximum. In this next example, I am investigating inconclusive tests, so I know what the outcome is going to be, seeing as that's the title of the example. However, I need to find my partials, and so that I can find my critical point, and then I need to find that value of that discriminant. So I've got the one sole critical point. Now I'm going to take the second partial with respect to x and second partial with respect to y, write that down so that I can get that discriminant and determine what those values are at that point 0, 0. Now notice when I go to plug in my value 0, 0 for all of these different partials, I'm going to end up with a 0, which means that my test is inconclusive. So let's look at that picture and see why he might be listed as inconclusive. If I look at the picture, notice that the bottom of this particular shape that I'm looking at is flat on the bottom, and it is this flatness that makes that local minimum invisible to that second derivative test, and therefore it is inconclusive. So I'm going to look at my next little guy here, and I will take the partial with respect to x and y and whatnot. Alright, let's note that I'm trying to find my critical point here, and I know that's when these two partials equal 0, and when y is 0 it looks like x can really be any real number. So my critical point is then a0, where x is any real number. So let's try and get the value of, I'm going to go ahead and do my second partials, and then I'll get the value of that discriminant. Alright, what I'm going to get is 0, and once again the test is inconclusive. If you'll recall what we had to do to find the absolute max for min, we had to have a closed bounded set. And what I did was I found the local mins and max and found the value of those at those particular points. I found the value of the function at those particular points and at the boundaries, and then I compared them. It's going to be very similar here, or we are going to just do this, extend this into 3 space, taking the partials. Step 1 is complete. I found the value of f at my critical points. There was only one critical point, and I found that value. There it is. So that is for step 1. Step 2 says I need to find the maximum minimum values of f on the boundary of R. Now R is a circle of radius 2, and I'm going to have to check that boundary, those boundary values. So I'm going to write this in terms of different parameters. I'm going to go ahead and write x as 2 cosine theta and y as 2 sine theta. And I'm going to state that theta is in between 0 and 2 pi. Now in writing it in terms of theta, I have now written this equation in terms of just one variable, and that's going to make things a lot easier when I'm checking this boundary. So I've got my new equation in terms of one variable. I'm going to need to find the derivative at that point so I can find the corresponding critical points for this function. I've now found the critical points for a new function g, but I'd like to know what those are in terms of x and y, so I'll just take this negative pi over 4 and plug it in for both of these and get an xy point. Okay, so here are my x and y points for my critical points on the boundary. Now what I need to do is find those function values. So I'm going to plug this in, each of these points, into my function and get that function value at that point. And just still working on step 2. Alright, I've now done my step 1 and step 2. Now I need to look at those function values at all of those critical points, and I find that this point here is my maximum, and it happens to occur at a boundary point, and this point here is my absolute min, and I meant to say absolute on this. This is my absolute max, and this is my absolute min. This occurs at an interior point, and this one occurs at a point on the boundary. Lovely. Alright, I am using my second derivative test here and found that at that critical point 0, 0, I have, doing my comparison here, I have number 1 on theorem 1314, which tells me that 0, 0 is a local maximum. So now that I have that it is a local maximum, I'm going to check and see what I've got going on here, and I find that when I rework that equation in terms of the one single variable theta, I get that my function equals a constant, and then my derivative is then equal to 0, and which means that I have my critical point at that 0, 0. So not only do I have 0, 0 being a local maximum, but I also have it being a local minimum, and what happens is my function decreases from that point 0, 0, going towards that value of 3, but never quite reaching 3. And because this boundary is non-inclusive, that means I don't have any absolute minimums along this F. In this next example, they're asking me to find a point that is closest to another point. So find a point on this plane that's closest to this other point, which is going to involve minimizing the distance formula. So let me get that written out. So here's my distance formula. Now it's going to be easier just to minimize d squared, so I'm going to write this in terms of just d squared, and then I'm going to be finding my critical points. After that I will make massages, make it look a little bit better, and then I'll be finding my partials in order to find my critical points. Alright, after finding my partials and then setting them equal to 0 and finding my x and y, I found that my critical point is 4, 3, negative 4, 3. Alright, next thing I need to do is I need to figure out, is this a, how do I get this to be a minimum? Using my second derivative test, I found that my discriminant is positive, is greater than 0. My second partial with respect to x is greater than 0. This means that I am indeed at a local minimum value. So this is a local min. Alright. Now we don't have any boundary to check this over, so what we would have to do is kind of look at the function and argue it geometrically. They wanted me to find that point, so I will be plugging in this 4/3, negative 4/3 into my original and getting the value of that point, and then looking at the picture and stating it must be the minimum because of the symmetry of the three-dimensional figure. And there we have our point. And that's all for this one. Come see me at the Collaborator. Email me if you have questions.